Hello everyone, I'm going to explain chemical oxygen demand as a parameter that can be used for characterization of water, wastewater, and sometimes also it can be used for other waste, like solid waste or municipal solid waste basically. But of course you have to be careful with the dilutions that you are applying for this kind of solid waste, okay? What is chemical oxygen demand? Always we refer to it as COD. COD here is defined as, or the chemical oxygen demand is defined as the amount of oxygen equivalents consumed in a chemical oxidation of organic matter by storing oxidant. Always we use potassium dichromate, K2CR2O7, and this is, of course, this is used in the standard method. It can be used again to measure the pollutant in water, wastewater, and waste, as I mentioned, and you have to be careful about the range. It also can be used for characterization as total COD, means that you don't actually filter the sample if it's liquid. You don't filter it, just take a sample and put it in the test tube and put the oxidant or the storing oxidant, in this case the potassium dichromate, and then the test consists of refluxing this sample for 2 hours in the presence of the amount of oxidant, and then the concentration of organic matter in terms of oxygen equivalents can be determined from the difference between the initial and the remaining oxidant concentration in the sample after the 2 hours. So again, this is just standard method. If you just get any standard method for water and wastewater characterization, you will find it actually standard there, standard method with different steps and what kind of devices or apparatus that you need to do this. Back to this kind of filtering the samples. Again, you can actually just take the sample as it is. Say, I'm going actually to take 1 ml of water and put this certain amount of dichromate. In this case, I will actually get the total chemical oxygen demand. Or if I'm actually interested in filter sample or filtered sample dissolved COD, in this case, I can use some kind of filter. I can maybe point to micrometer filter paper, and then in this case I get actually dissolved COD, or sometimes also I can use 0.45 as cut off paper for this dissolvent. So basically you can refer to the standard method and see what kind of paper filters you can use and what is the definition actually exactly for the filter paper or the dissolved chemical oxygen demand. This is just give you some kind of overview about the method. I'm not going actually to explain how to do this test in the lab, but this is just to give you the main idea. But I'm actually here today to focus on how to calculate the theoretical chemical oxygen demand. Theoretical means that if I'm actually if I know the chemical formula of the material of the waste, I can actually calculate theoretically how much oxygen I can get. I need to oxidize this material. For example, if of course the glucose may be not actually a waste, but this is just a standard compound that we can use to calculate this chemical oxygen demand. And if we have this kind of formula for glucose, we have C6H12O6. So how much oxygen I need? I need actually, if I have 1 mole of glucose, I would need actually 6 moles of oxygen to oxidize this material. So in this case, how much chemical oxygen demand? In this case, I need actually to calculate how much amount of oxygen I need 6 moles per mole. So in terms of grams, I need actually 6 times the molecular weight of the oxygen, 32. In this case, I need actually after simplifications, I will get 1.07 gram COD per gram glucose. Of course, if I have other materials, or I have other waste with known formula, I can actually use the same equation to calculate it based on the stoichiometry. I need actually to make some kind of balance and get the based on the composition. How to do this? Here, this is a formula. Here, if we have a material or a waste or any chemical compound with CaHbOcNd, which means that I have number of A, B, C, D is number of atoms of each of carbon, of hydrogen, of oxygen, of nitrogen, respectively, and how many moles of oxygen I need to use to oxidize this material. I can actually have this kind of balance. I need to have A, number of atoms of carbon, plus B, number of atoms of hydrogen divided by 4, minus number of atoms of oxygen divided by 2, minus 3, number of atoms of nitrogen divided by 4. This gives you how many moles of oxygen I need to completely oxidize this material to carbon dioxide, to hydrogen, to water, and then of course I will have some kind of ammonia produced in this case. Okay, so this is really important because basically again, if I know the composition, I can just type this equation and get the composition, get the amount of oxygen that is needed to oxidize the material completely to the final product, in this case carbon dioxide and water and ammonia. How about this? Actually, in literature, you can find this always. If you read literature about the anaerobic digestion, people actually cited that 1 gram of COD equal to 0.35 liter of methane. This is always the case. Or sometimes also people say each liter of methane need 2.85 gram of oxygen or chemical oxygen demand. How can we get to this number? I will explain to you how to do this today. So if I have 1 mole of oxygen of methane, I need 2 moles of oxygen and to produce carbon dioxide and water. So basically this is a final. Again, if you look at the previous one, I don't have nitrogen. In this case, just the final product will be carbon dioxide and water. Is this true? Let's see. So what do we have here? We have here now, we have I have how many carbon atoms I need? I have only 1. So basically, if I have A equal to 1 here, and I have oxygen is equal to 4, so plus 4 is number of atoms of hydrogen divided by 4. Do I have C? I don't have C. So basically, I have number of C. There is no oxygen in methane, of course. So basically, this term will be 0, and I don't have nitrogen in methane, so this term is of 0. So basically, this ends up to 2. So basically, this is correct, right? So basically, this 1 plus 1, this 1 plus 1, 4 divided by 4 is 1. So basically, you have 2 moles of oxygen here. Okay. So basically, the left-hand side is balanced. So basically, I have C 4 H4 C 1 only carbon and H4 which is methane, and plus 2 moles of oxygen give you what? How many moles of oxygen of carbon dioxide? It will be 1 mole. So basically, I have A in this case is 1, right? A is number of atoms of carbon in methane is 1. So basically, I have only one mole of carbon dioxide. And then how many mole of water? It will be 2. So how can we get this one? Again, B is 4 here. This is basically B, number of atoms of hydrogen. So basically 4 divided by 2 minus 3D, we don't have nitrogen, so basically this term is 0, completely 0. So in this case, this is just a 2, and this is why I have 2 moles of water here. Okay, so basically this is just to give you application of the equation that I just mentioned in the previous slide, and in this case I have this balanced equation. In this case, what we need to do now is to go back to the stoichiometry and calculate why I see this in the literature. 1 gram of COD equal to 0.35 liter of methane. Okay, how to do this? Okay, let's go in a little bit details here. So basically, again, from this previous one, I have CH4, I have CH4 plus 2 moles of oxygen equal to 1 mole of CO2 plus 2 mole of H2O, correct? This is just from the previous slide, okay? So now, what does it mean? This means that 1 mole of methane need 2 mole of oxygen. So basically, I need 2 moles of oxygen, which in this case also what is this COD, right? This is oxygen here, this COD. 2 moles of COD bear 1 mole of CH4, correct? So basically this is just here, 2 moles here per mole of methane. Okay, what does it mean if we need to have to convert these moles to grams, for example? So 2 moles of oxygen, how many grams? Each mole of oxygen 32 grams. So basically 2 moles of O2 times 32 grams of O2 per mole of O2, correct? So basically after simplification, this is divided by 1 mole of CH4. I could also do the conversion for methane here in terms of gram, but just to put it aside now, because I'm interested in actually in volume, and I will come to this a little bit later. So basically what we have here, so from this one we have, this is actually a simplification as I mentioned. So basically this can be simplified to 64 just a second, please. So I will have 64 what? 64 gram O2. Again, this is O2 what? This is basically COD, right? Oxygen here is the chemical oxygen demand per mole of CH4. Okay. Okay. Our goal is what? Is to calculate how much COD is needed by a liter of methane, right? So and as you know that the molar volume equal to what? Equal to 22.41 liter of any gas. So basically, if I assume actually here the methane is ideal gas, so means that each 22.4 liter of methane occupy 1 mole or 1 mole occupies, sorry, 1 mole of methane occupies 22.41 liter of methane. Okay, this at of course, don't forget this one, at standard temperature pressure, which here this is standard temperature pressure is 0 Celsius. Temperature is 0 Celsius and 1 atmosphere. Okay, 1 atmosphere. Sorry, this is really bad one. And 1 atmosphere again. So, okay, this is 1 atmosphere. Okay, atmosphere. Just the pressure actually under this what does it mean ASTB. Okay, go back to our or yeah, you can actually also say 0 Celsius or 1 Kelvin. It is actually 273.15 Kelvin. Basically, if you convert between Celsius and absolute temperature. Okay, so go back to our calculations again. So if I have this one here, if I can have this equation back here, so basically this equal to 64 gram oxygen or chemical oxygen demand again per mole. Again, this is what? 22.41 liter per mole, liter of CH4 per mole. CH4, of course. And of course, we have here, this is still 1 mole, right? This is basically 1 mole in the denominator here. This is 1 mole CH4. So give us, actually, after, if we simplify, this means that we need to have 64 gram COD, which is, again, actually, I refer to oxygen or chemical oxygen demand from the beginning is this the same actually, because basically we need oxygen to oxidize the methane in this case. Okay, divided by 22.41 liter of CH4. Okay, what does this mean? This means that we have to have this maybe also can be simplified more to have something like this equal to 2.85 gram. Just see, let's just a second, please. So this means that we have to have 2.85 gram of COD per liter of methane, per liter of methane. Okay, CH. Okay, again, what does this also mean? If I need actually to have, this is basically mass of COD per liter. In our we need actually how much liter of methane per gram of COD. Basically, if you reverse this one, this also can give you the fact that 0.35 liter of methane is equivalent to 1 gram of oxygen or 1 gram of COD. This is why actually in the literature, so in this case, again, so you can have actually this, this is the meaning here that I have 2.85 gram COD per liter of methane, and this gives us the after simplification, which means that 0.35 liter of methane, this is liter of methane per gram COD, or maybe 350 ml of milliliter of methane per gram COD. I hope this is actually explains this well, and I would like to thank you, and don't forget to subscribe to the channel and share it with interested people. With that, I would like to end here, and I welcome any comment. Thank you. Bye-bye.